Welcome to this lesson on sketching transformed exponential functions. In this video, I will assume that you are familiar with the basics of transformations and the terminology involved in the process of transforming a parent function. My goal is to show you two methods for sketching the graph of an exponential function that has been transformed. I will demonstrate how to use the mapping rule method and how to identify strategic x values to gather enough points to sketch the graph. I will also discuss how to find intercepts and provide examples to help you better understand the concepts. Let's take a look. Before we begin this discussion, I will assume that you already watched a video that carefully explains how applying the four common types of transformations to a parent function affects its shape. So here, I will assume that you are familiar with that and with all the relevant terminology of transformations. If you haven't watched that video, I will have it linked in the description box below. We will start by assuming that y equals f of x is a parent function and that the point mn is a point on the parent function f of x. We will also assume that g of x is a transformation of f of x. So notice how g of x is expressed in its general form, where we can see all four parameters a, k, c, and d involved in the transformation process. Again, I am assuming that you are familiar with these parameters. If not, when you watch the video that I am linking below, you will understand their role in the process of transforming the parent function onto g of x. Our goal in this lesson is to sketch the graph of an exponential function that has been transformed. I will show you two ways to sketch transformations. The first way will be the mapping rule method. With this method, we must take a point mn on the parent function, and we must identify the parameters involved in the transformation. In this general form, I have all four parameters. They are highlighted in red, A, K, C, and D. In order to obtain the coordinates of the new point on the transformation, often called the image point, we then apply the parameters to the original point mn as follows. We multiply m by the reciprocal of k, right here. And we add c to this product. This will give us over here the new x value. To obtain the new y value right here, we multiply a and n, and then we add d. And in this way, we obtain the point on the transformed graph. This is the entire point. The second way for sketching such functions will not include a rule. Instead, it will focus on identifying strategic x values, including intercepts, in order to gather enough points to sketch the graph. I will show you exactly how to do this in my second demonstration. Now let's go ahead and consider an actual function that has been transformed. Our goal here will be to sketch its graph using the two methods. But in order to sketch, we will need to find actual points on the graph. I will show you full calculations for finding the coordinates of such points. I know that often we are allowed to use a calculator, in which case many of the steps that you will see here will seem redundant. However, it is never wrong for us to know how to get these values completely on our own if it ever becomes necessary. First, I will show you how to get points on the graph using the mapping rule method. The first thing that we are going to do is to extract the parent function from here. See, the parent function was not given to us explicitly. It is our job to determine what that parent function should be. And if you remember, the general form of the parent function is just simply y equals b to the x. So what we need to do here is to determine b, the base. But we can easily do that just by looking at the transform function. Look, here is the exponent, and the exponent is always on top of the base. The number right next to the exponent is the base. That number is 3 right here. So then I know that the parent function will be y equals 3 to the x, just like that. My next goal here now is to determine the expression for my mapping rule, the rule that I will apply to get all of the new points. But in order to do that, I have to determine the 4 parameters, A, K, C, and D. And they are right here. So for example, notice 1/2. I'm going to go here. 1/2 is A. So A is equal to 1/2, just like that. Then this number right here, -2, the number that is right outside of the set of brackets, is always K. So I know that this number here will be K. K is equal to -2. Let me rewrite it right here next to A. K equals -2. Now, I want you to notice that the expression inside of the set of brackets, x plus 5. Now, if you remember, when we write the general form just using A, K, C, and D, right here, what we really typically see here is something like this, x minus c. And right now, I don't see x minus, I see x plus. Well, that's because c is negative. That's because what we really have is x minus -5. So then this really says that c is a negative value. So I'm going to write c equals -5 right here. And then finally, right there, the constant is the value of d. So then I'm going to write here that d is equal to -2. And in this way, I have all 4 values. So now I'm going to take these values and I will incorporate them into here. So if you notice, the new expression or the full expression will go as follows. We are starting with 1 over k, the reciprocal of k. Now, k is -2. So 1 over k is like having 1 over -2, which simply speaking, 1 over -2 is -1/2. So I'm going to write here -1 over 2 times m. Now we have plus c. C is -5, so that will be -5. And then we have over here a times n. A is 1/2. That means that we're going to have 1/2 times n plus d. And d is -2, so -2. And here it is. This is now the expression that we will apply in order to get the new point. Again, mn is a point on the parent function, the base function. Then we apply this formula or this rule in order to get the image of Mn. The image of Mn is this point right here, which is a point on the new graph. I want to emphasize that this here gives me the new x value, and this expression here gives me the new y value. Now here, notice how we have the parent function, y equals 3 to the x. That hasn't changed. We're working with the same function. And we see 5 points. And these points are points on the parent function. And the way that I found those points was quite easy in a sense. It's like creating a table of values. You pick a few x values. Imagine -2, 0, 1, 2, and 3. And then you take those x values and you substitute them into the x of the function. You do the computation and you get the point. I want to show you exactly how I got this point right here. I'm going to do this on the side. So for example, x is -2. That means that y will be 3 to the -2. 3 to the -2 is 1 over 3 squared, which is equal to 1 over 9. And very quickly, I now know that -2, 1 over 9 is a point on the parent function. And what I want to do now is to figure out, well, what is the image of this point? Under my transformations, where will this point land? And it's going to land on the new graph. So I want to find the new point. In order to do that, I will show you how to apply now this formula right here to get the image of -2, 1/9. So let's go ahead and do that. So here, starting then with -2, 1 over 9. And I want you to think of -2 as m, 1/9 as n. And then applying the transformation, we're going to have -1/2 times -2. Then -5, 1/2 times n, 1 over 9 minus 3. So there we go. Then simplifying. And first of all, a negative times a negative is a positive. 1/2 times 2 is going to give us 1. So this will be 1 minus 5, comma. And now here we're going to have to multiply fractions, and we multiply two fractions by multiplying numerator times numerator, denominator times denominator. So 1 times 1 is 1 over 2 times 9, 18 minus 3. And because I know that I'm going to be simplifying and I'm going to continue algebraically, I'm going to need a common denominator. So right away, I'm going to put this over 1. And I will multiply top and bottom by 18. So that's what I get. And then here we're going to have -4. That's the new x value. And then my common denominator 18 and 1 minus 54. So that's that point. I will continue down here below like this. So now we are going to have -4, -53 over 18. And there is the image. This is now a point on my function f of x. This point was mapped onto this one. Because I'm going to be sketching, it is a good idea to approximate this fraction as a decimal. So then you can do this with your calculator. -53 over 18 is approximately -2.94. Okay, right there. So there is our point. Here you can see the same calculations that we just derived for the first point, and we will now follow the same approach in order to find the image of the other 4 points that we have here, these 4 points. Here you see that I am applying the same mapping rule and following similar computations to obtain the image of 0, 1. This is the image here. Similarly, with the point 1, 3, you can see the calculations and you can see the image here. With the point 2, 9, similar calculations and the image of 2, 9. And then with the point 327, calculations right here, and then here is the image. Here we see all calculations and the image points all at once. We see everything together. Now we're going to go ahead and put all the points in the XY plane. Well, in your case, you're going to plot the points on the XY plane. But I'm going to start here with the horizontal asymptote. If you remember, the horizontal asymptote was the line y equals -3 because the horizontal asymptote is always equal to the d value in the transformation. So in this case, we're going to see it right here. You can see it, the horizontal line, that's the asymptote. And then we should always label the asymptote as the line y equals -3. Now let's go on to the function. These are all the images that we found through the mapping rule method. So I decided to use those points because we generated several points in there. So again, from the mapping rule method, these are the points that we generated. I'm going to go ahead and plot them. There they are. And now you would actually, if you were doing this with pencil and paper, you now just gently trace through those points to get your graph. So in this case, we're going to see it right here. See how the graph nicely passes through all of those points. Okay, very nice. And you can see how it approaches the horizontal asymptote as x goes to positive infinity, exactly as we expected. I'm going to go ahead and label the graph right here to make it super clear that this is the expression, or this is the expression for this particular graph right here. So now, folks, this is a completed graph. Always remember to label the axis. Along the x-axis, we're going to put an x over here and a y. So now you can beautifully see how your horizontal axis has been labeled as the x-axis and the vertical axis has been labeled as the y-axis. This is what is considered a fully labeled and completed diagram, where all of the important objects have been labeled, the points are plotted in there nicely, and you have given a sense of scale. Along the x-axis, you're going by 5s. Along the y-axis, you're also going by 5.